Okay, now let's look at friction forces. Friction forces always act in a direction opposite to the direction of motion. So if the object is moving in this direction, that's the direction in which the friction force acts. If the object changes direction and moves like that, the friction force will be in the opposite direction. Okay, in this diagram you see here, here's the puck on a horizontal surface. There's the weight of the puck, there's the normal force balancing the weight, and it turns out that the friction force is always proportional to the normal force. And that proportionality constant is called the coefficient of friction. So the friction force, in this case the subscript K denoting kinetic friction force, is proportional to the normal force. Okay. The friction force depends on the two types of surfaces in contact and is independent of the area of contact. So if as long as the two materials are the same, roughly speaking, the size won't matter. The friction force is only proportional to the normal force, which is the weight, which is equal to the weight in this situation. And you can see that the friction force is also independent of the velocity. Part of the friction force is because the surface is in contact. Yeah. Much of this is due to the attractive forces between the molecules of the two objects. So the attractive forces of these molecules that are quote unquote touching each other. So in fact, perfectly smooth surfaces of similar material would adhere, forming a cold well. Okay. All right, so here is in this diagram we show you a static friction force. So for instance, in this problem, in this diagram, if you're trying to push the crate in this direction, and if the crate does not move, there must be a static friction force despite lack of motion. And there's the static friction force. And it turns out that this static friction force, the maximum value of this static friction force is greater than the kinetic friction force, the friction force that arises when this object is in motion. So let's illustrate both the static and kinetic friction force. So imagine this box and you push this box horizontally in this direction, and if it does not move, then that means there is a static friction force. And you find that if you keep increasing your force, the object will not move until you apply a minimum force required to get it moving. So you can surmise that the static friction force can be anywhere from 0 to a maximum value. And that's what's shown here. The static friction force, you apply a force like this, and that's the static friction force. There's on this axis we plot the applied force. And so the static friction force matches the applied force. The static friction force is equal to the applied force till the maximum value is reached. And then this breaks loose, and once it breaks loose, the kinetic friction force is less than the static friction force. So the kinetic friction force is always less than the maximum static friction force. Okay. And that's what this diagram is showing you. See, there is this maximum static friction force, and there is the kinetic friction force, which is less than that. So it turns out that, so you see when two surfaces are in contact, no matter how smooth the surface, the rough surfaces, because of the roughness of two surfaces, the actual area of contact, interestingly, is when two surfaces are in contact, the actual microscopic area in contact is of the order of 1 part in 10,000. All right, so now let's say you're skiing downhill. We'll represent you by a point. Here's your weight, and the most useful components, well, the most useful thing to do is break down the weight into a component parallel to the slope and one perpendicular to the slope. Okay, and as you've seen many times before, this component is mg sine theta, where theta is the angle of the incline, and this is mg cosine theta. Alright, so in this problem there is the skier, there's the weight, there's the component of the weight, and along the slope, component of the weight perpendicular to the slope, and so the normal force is equal to that. And if there's any friction force, the friction force is in that direction, assuming the skier is skiing down. Here's a heavy crate on a truck bed, and now a heavy crate on a truck bed can be dangerous during braking, and we'll come to that in a second. So let's say here's the truck, and if the truck accelerates, the only thing that the crate is in contact with is the truck bed, and so the friction between the crate and the truck bed is what the static friction force is, what provides the force to accelerate the crate. And of course, if for some reason the static friction force is not large enough, and if the acceleration of the truck is too large, this crate will be left behind. Okay, so of course, in real life, if your crate is rather heavy and the truck bed is smooth, then you chain it down. But anyway, now let's talk about the other situation. Let's say if a truck gets into a wreck or something, and then it will have a large acceleration in the opposite direction. That would mean that the friction force has to, you have to have a static friction force in that direction to prevent the crate from sliding along in that direction, along towards the cab. And if this force needed is greater than the maximum value, then the truck bed, this crate will start sliding, and then this people in the cab are in danger. You already hit something in the front, and then this can come and crush you too. So you have to be real careful of that. Now let's look at objects describing uniform circular motion. So let's say you're driving on a circular road of radius r, and if you're driving in a circle at speed v, what you need is a centripetal force in that direction, and the centripetal force has to be equal. The centripetal force you need is mv squared by r, where r is the radius. V squared by r is, of course, the centripetal acceleration. Okay. So, for instance, if you were driving on a flat road and there is the center of the circle, you need a centripetal force in that direction. The centripetal force, the maximum value of the centripetal force is mu s times the normal force. The normal force on a flat road is equal to the weight. Okay, and so the maximum, so let's do it. So the maximum centripetal force you can have is mu s times mg, which is equal to mv squared by r. So for a given radii of the road, that means you can only have a maximum maximum velocity, and if you drive faster than that, you'd slip. By the way, on a flat road, the centripetal force is provided by static friction, since the car is not moving in that direction, and so you're leaving rubber behind on the road. So now to prevent that, so your tires would wear faster. To prevent that, we bank roads. Okay. So now, if you bank a road and there's the center of the circle, you need a centripetal force in this direction. Now here's what will provide the centripetal force. So the normal force, the force that the road exerts on the car, is in that direction. It's perpendicular to the road. This component of the normal force will balance the weight, and this component of the normal force will provide the centripetal force. So let's say, so in the case you're let's say you're driving at the right speed for this bank. Let's figure out this. So um, actually we got it here. Uh, so there's that component of the normal force, which is n. That component of the normal force is n cosine theta, which is balancing mg. And this component of the normal force, n sine theta, is providing the centripetal force for that speed. So if you move faster than that, that component of the normal force is not enough. That the normal force, the value of the normal force is set by the weight of the car and the angle of the incline. Okay, so if you drive faster than that, then you'll actually end up needing a static friction force in this direction. Okay, so for speeds greater than the speed, the speeds greater than the speed implied by this equation. Okay, so we'll assume that we don't need the static friction force. Okay, and then if you divide this equation by, if you divide this equation by this equation, what you get is tan theta, and tan theta equal to p squared gr. So what we are saying is, for a road that's inclined at angle theta, if you drive at this speed, r is the radius of curvature, if you drive at this speed, you will not need any friction force. And the normal force component, the horizontal component of the normal force provides the centripetal force. And that, so static friction forces are zero, saving the nation billions of dollars on wear and tear of tires. Okay. That's why we bank our highways. So similarly, if you want to turn a plane, you have to bank the plane. You could not turn a plane if it were flying horizontally. Okay. The lift is perpendicular to the wing, and this component of the lift provides the centripetal force. Here's a ride, a fun ride that most of you have probably experienced, the gravitron. And so when the floor falls off, there's a static friction force that's holding you up. And you know that the static friction force, the maximum value of the static friction force is mu s times the normal force. And in this case, the normal force is what's providing the centripetal force, okay, for you to go in a circle. So it's equal to mu s times mv squared by r. So here's the maximum static friction you can have. Okay. And so no matter how slippery clothing you're wearing, you can make a rough estimate of the mu s, and you just have to make sure that the gravitron is spinning fast enough such that this is greater than mg, and then the person won't fall down. So here are some coefficients of friction. The static coefficient of friction, for these friction coefficients depend on surfaces. So for instance, this shows you for rubber object on dry concrete, mu s is 1 and mu k is 0.8. Rubber on wet concrete is 0.7 and 0.5. So these are relevant numbers for driving conditions. Rubber on dry concrete, higher mu s is smaller your stopping distance. So when it rains, your stopping distance, since mu s decreases, your stopping distance increases. Okay, and again, what these numbers mean are the following. So if you have an object that weighs 100 newtons, so if this object is rubber on dry concrete with mu s equal to 1, well, with mu s equal to 1, the maximum static friction force is mu s times mg, which is 100 newtons. So the force you would need to get the object started will be equal to maximum friction force, which would be 100 newtons. Okay? So what these numbers mean is if mu_s is 0.7, to get the 100 Newton object started, all you need is 70 Newton force. For wood on wood, mu_s is 0.5, so a wood block sitting on a wooden surface, you need 50 newtons to get it started for a 100 Newton block. That's what these numbers mean. All right, we'll pause here.